again, my name is Kikuchi of Keysight expert. And I'll talking on the topic of high-performance control systems and EDA solution for state-of-the-art quantum computing. First, let me introduce our company, Keysight Technologies. We spin off from the Hewlett-Packard, which was started in 1939, and 1999 we became Agilent Technology as a spin-off from HP and became the premier measurement company. In 2014, the Keysight became spun off from Agilent further and became an independent control-focused electronic measurement solutions. All in all, more than 80 years of innovation leader in electronics and software. So this is the agenda I have, and I will talk about the quantum EDA solution and also quantum control system, which we released last year. These are the two I'd like to introduce today. First, the quantum EDA at Keysight. And our quantum EDA strategy include the translating quantum parameters into EDA design so that the microwave designers can take advantage of quantum computing. Our tools basically has a very high market share in the planar circuitry, and one of the quantum approach is a superconductivity quantum. So we believe our technology really fits well, and QA and qubit design we are designing to promote that, and we incorporated Josephson circuitry in 2022. And on the right-hand side, from single bit to several bits, we have our tools laying out and using our software and qubit development and simulations and their layout and nonlinear and EM and also analysis of EM. All these essential design elements can be supported, and thus meeting the large market needs. And our EDA solution has its core ADS, Advanced Design System. ADS leads the market as a high-frequency design methodology, and it can cover the very simple design to very complex design and RF and microwave components, and from communication to aerospace and defense applications and MMIC. So whole variety of design development can be supported. And ADS, as you can see, the very intuitive schematic input and the components layout leading to the design simulation and entry and the simulation, and also works with the schematics with ample component library and supporting two types of solvers, and thus can work with the circuitry and in its EM electromagnetic analysis. And the simulation result can be analyzed with many function groups with a good outcome result display as well. And the most recent version, ADS 2024, will support the superconductivity quantum bit design flow. And in this flow, the superconductivity schematics can be designed from scratch, and for that purpose, quantum qubit component is embedded into the design level, and layout can be automatically generated from schematic. And the superconductivity design, circuit design, has the challenge of as the number of bits goes up, the electromagnetic simulation becomes very complex. ADS provides an intuitive analysis setting for electromagnetics. And once you set the electromagnetic analysis right, and you can use the model in the ADS Quantum Pro and carry out the analysis. And Quantum Pro provides the FEM and also moment method as well, which solves the surface current, metal surface current only, and thus reducing the time needed substantially. So large circuit can be processed very quickly. And based on the frequency response from the analysis, the resonator and qubit parameters can be extracted. And with this extracted parameters, you can go back to the circuitry to make some adjustment and corrections. And dimensions are parameterized, so you can easily work with the schematic, and until you get what you want. And once the result is satisfactory to you, you can export the design to GDS file and move to the production. And ADS has a nonlinear solver, harmonic balance nonlinear solver, and nonlinear co-simulation supported in order to have a very efficient design. And it brings efficiency to the quantum amplifier, and which is a very important component to get the quantum system output tuning. And from several to 1,000 J2WPA workflow is supported by this harmonic balance solver, and the currency can be uniform or flocking type. And on the left hand side, both types are shown with optimization. And for nonlinear simulation and quantum bit nonlinearity can be very accurately predicted. And so nonlinear and eigen analysis are combined so that the frequency shift can be accurately predicted when the power goes up. So now we're going to talk about the qubit control. And in the leading edge, quantum computing has three challenges, as shown here. The high fidelity gates and readouts and scalability and feedback and quantum error controls. First, about the control requirements for high fidelity gates. As you can see, the clean signals and high precision stable tones and high precision virtual Z gates that need to be achieved. First, for the clean signals, let me explain. The superconductivity quantum bit has a carrier sequence of several gigahertz, and that has to be modulated in the microwave form. And typically, the IQ signal is DA converted and up convert, and with the IQ modulator, and with dynamic resonance takes place, and as a result it can have increased errors like a cubic crosstalks and leakage. And to solve this we use the digital conversion for modulation instead of the IQ modulation, and then convert it to DA converter, and then output directly. And this way, you don't have the leakage, no crosstalk like this, as you see on the bottom, on the right bottom. And in order to make this possible, as the custom very fast DA converter was developed, and the world's first fully digital quantum control module was developed. It's called M5300A and has a DC to gigahertz, very range of the output, and its compact form factor. It has a 4-channel microwave output capability, and this direct digital synthesizers generate very exact tones and stable tones. And this M5300A uses the Xilinx Vertex Ultra Scale Plus, and use that with the AD converter and custom DA converter, and for up conversions and DA convert and then output directly. And within the DA converter, NO becomes NCO phase 32 bits, and frequency 48 bits, very high in both cases. And no drifts due to temperature or aging, because all in digital. Such high precision signal processing results in a very good analog clock, and well, still phase stability is limited by the DAC and the analog clock performance phase noise. And best analog phase noise performance for stable tones, we generated get the very top notch frequency reference, and which is used for sampling clock for digital converter. And this way, very high performance SPGA gateway and world-class analog phase noise were combined to obtain the high precision and stable tones. And the third topic is about the high fidelity gates using decomposition and virtual Z gates. And we developed the parametric FPGA native gate primitive. Using this, the qubit amplitude and frequency and phase are applied and controlled real time. And as for the virtual Z gates, by moving the phase, we can control that. And for frequency, that the phase continuous and phase coherent frequency change can support that. And NCO phase can be controlled with the 32 bits, and combined with the world-class analog phase noise performance, we obtain a very high fidelity virtual Z gates. And then the second need, which is the high scalability needs. And for the qubits, existing electronics cannot extend that. 4K electronics was developed. However, that still is not enough to obtain a very high scalability. For example, let's say 1 million qubits, and 4K electronics chip, and between the classic chip and the quantum chip, we need 1 million cables, which really does not fit. And mil-Kelvin system on chip and SoC, mil-Kelvin SoC resource, and because of the power consumption, it just does not support the 100 signal lines. And as a result, for quantum bit control, and we'll need to have a novel, different control technology such as multiplexing, for example, frequency division multiplexing, or time division multiplexing, which we need to start looking into for the future. And in order to support the scalability, we have decided to make our system modular with a very small footprint in a chassis form factor. And with the increase of qubits count, and we can add more modules, and this is a minimum, and about 3-bit is supported. Superconductivity qubits are supported, and this because it is modular based on the needed qubit count, we can support more than 1,000 qubits supported like this. And we have 2 gigahertz and for the future, when there's a large-scale need, we can still support that. And these modules are all industrial grade, so both commercial and the research purpose, we can support both purposes. And for controls and high fidelity implementation, we need to talk about the feedback requirements. And the qubits, error correction, and active qubit reset needs feedback. For that requires, we need a very low latency communication amongst modules. And to support such inter-module support, and Keysight intra-chassis communication and inter-chassis communications have been achieved, like in left-hand side within the chassis, and inter-module communication uses the backplane 1.2 gigabps star-type wiring, and this we can digitizer to AWG broadcast possible, and on into the RF waveforms. And as I explained earlier, using FPGA, we have game primitives combined with this, and thus we have a we can update the waveform on real-time basis. And as the qubit number goes up, and we have many more modules, as we have, we can support that by inter-chassis communication. And 7.2 gigabps lines will support either daisy chain or star topology. As you can see on right upper corner, up to 26 chassis can be connected in 2 hops. So more than hundreds qubits can be supported with a very low latency. That's all I have to present. Thank you very much for your attention.